Staring at a circuit diagram for the first time can feel like trying to read a foreign language. You're looking at a tangled mess of wires, a dozen different variables, and branching paths that seem to go everywhere at once. If we zoom out from the classroom, these diagrams look different. These symbols are actually descriptions of how the physical world is wired, unbreakable laws that govern everything from a smartphone to a star. In the 19th century, physicist Gustav Kirchhoff realized that the same logic we use to track heat and pressure applies perfectly to electrical networks. He realized that electricity follows two basic realities. The amount of stuff entering a space must eventually come out, and every step taken uphill must eventually be balanced by a step taken back down. When you lean on these two intuitive rules of conservation, the most complex circuits stop looking like a math puzzle and start looking like a simple balance sheet. To understand how current moves, think of cars on a highway. Matter cannot simply vanish into thin air, and it can't pile up in one spot forever without causing a total standstill. If we map that highway junction onto a circuit schematic, we find what's called a node. This is the exact junction where multiple wires meet. Electrons carry a negative charge, so they naturally repel each other. Because they're constantly pushing away from one another, they can't park or pile up at the node. Every electron that flows in must instantaneously push another one out. This diagram shows a complex node labeled A. Kirchhoff's current law tells us that if you add up every bit of current flowing into this point, it will exactly equal the amount of current flowing out of it. To keep the math organized, we treat these directions like a bank statement. We give inward-facing currents a positive value and outward-facing currents a negative value. As long as you stay consistent, the total will always balance to zero. This is the conservation of charge, a physical guarantee that no matter how many branches a circuit has, the system does not leak. While current is about the flow of electrons, voltage is about their potential energy. To visualize this, it helps to stop thinking about flow rate and start thinking about height. Imagine a hiker starting at base camp, or 0 volts. To get moving, they take a mechanical ski lift, our battery, all the way to the summit. The hiker can take a dozen different winding paths to get back down, but once they arrive back at base camp, their total change in elevation for the whole trip is 0. They are exactly as high as when they started. Kirchhoff's voltage law applies this to electricity. It says that if you travel in a complete circle around a loop, the total of all your voltage rises and voltage drops will always add up to 0. To get the math right, you just have to track your own path around the loop and compare it to the actual direction the current is moving. When your path moves across a battery from the negative to the positive one, you're gaining potential. You're riding that ski lift back up the mountain. However, if you cross a resistor while moving in the same direction as the current, you're losing energy. You're walking down the mountain, so you record that as a negative number. This is the conservation of energy. If this weren't true, an electron could travel in a circle and arrive back home with more energy than it started with, creating a perpetual motion machine that the laws of physics simply don't allow. Let's turn these laws into a quick checklist for your next project or exam. First, the current law. Focus on the nodes. Just like a busy highway junction, every single bit of current that enters a point must also leave it. Second, the voltage law. Focus on the loops. Just like a mountain hike, if you end up back exactly where you started, your total change in height is 0. And remember the sine rule. If you're traveling through a resistor with the current, you're heading downhill, so give it a minus sign. By balancing these nodes and loops, you aren't just solving for variables, you're using basic logic to see exactly how the universe balances its books.